Hi, my name is Kietzmann and I will present our poster Long-Range IoT is LoRaWAN an option for ICN. This is joint work from Dirk, Thomas, Matthias and me. We started investigating on this topic as a result of different success stories in the past in the field of ICN IoT, for example, ICN LoWPAN. Today we try to answer the question, can LoRa-based communication provide similar opportunities? Let's start with an introduction to LoRa and LoRaWAN. LoRa is a low-power, long-range radio technology, and LoRa is the network architecture on top. It is one of the few systems that defines a complete stack with special network designs independent of IP. The main use nowadays is transmission of sensor data over wide distances to a cloud at minimal battery consumption. LoRaWAN defines three operation modes for constrained end nodes. Class A is purely producer-driven. An end node sends an uplink packet, which can be received by any gateway in reach, and it opens two receive slots afterwards. This mode operates most frugal with battery resources and is the default deployment choice today. Class C operates similarly, but it leaves the second receive window open. In that way, an end node is receive able at all times, which causes to high energy costs. Class B allows reception of downlink without preceding uplink and intermittent sleep. This is achieved by opening periodic receive windows. However, Class B is not commonly available on deployed infrastructures. LoRaWAN includes infrastructure nodes. Gateways act as next hops for end nodes and form star topologies. They simply relay packets between end nodes and a central network server. The network server is responsible for packet deduplication and all kinds of routing tasks. Downlink routes are selected based on uplink meta information and address one responsible gateway. The network server pre-calculates schedules to end nodes to avoid wireless interference, and it has to satisfy duty cycle restrictions. A roaming specification describes how globally distributed network servers can interconnect, but still a single network server is chosen to manage end node access. The network server translates data to application servers, which act as user interface. These are often accessed using common application layer APIs, such as HTTP or MQTT. It is worth to say that payloads are encrypted on the application layer between application servers and end nodes. So how can we bring ICN to this technology? The most obvious solution is an application layer relay that translates between ICN and LoRaWAN by protocol conversion or by implementing the application server itself. A similar approach is specified by lightweight M2M protocol to run co-op request response over LoRaWAN. However, no benefits from an ICN routing system will apply in this scenario. But how about we slightly modify the standard LoRaWAN deployment in order to resemble ICN properties more efficiently? Network servers queue downlink packets, which stresses their change of use as ICN caches. Unfortunately, the network server is centralized, but what if we could decentralize it? For example, if one network server would be deployed on every gateway, the distribution of caches increases redundancy and reduces latency. However, we would rarely improve the constraint node performance by that, and a number of problems remain open. Most dramatically, the media access of LoRaWAN relies on a central network server, which would need a major redesign. Gateways blindly forward packets, which stresses the case for ICN, where origins of data are not relevant. So how about interconnecting gateways and equipping them with FIP, PID, and cache, while the network server remains centralized? In this way, an end node can benefit from in-network caches placed on next-hop gateways that might answer requests without forwarding to the wireless. Conversely, requests might be forwarded redundantly by reaching multiple gateways without hitting a cache, which can actually worsen interference. It still remains open, though, how the centralized scheduling approach and routing interacts with distributed gateways. In both the aforementioned solutions, we ignored that payloads are encrypted in LoRaWAN, which poses a huge challenge to ICN, where names are used for routing on any network node. Implementing LoRaWAN as an ICN requires a change of core security mechanisms. From our investigations, we conclude that LoRaWAN, and especially its centralized media access, conflicts with core ICN principles. We argue for an alternative to run ICN directly on top of LoRa. A decentralized MAC layer should allow all nodes to initiate transmissions. Since the long wireless range is more liable to collisions than personal area networks, the MAC must deal with wireless interference as well as device energy constraints. A native ICN network layer on top of the MAC promises additional advantages. It allows for node-to-node, multi-hop and mesh communication, which leverages forwarding and caching even on constrained nodes. Additionally, transparent access to the ICN layer allows forwarding by LoWPANs or infrastructure networks without the need of application layer gateways.